So good morning to all, especially to the panelists and to all our guests and viewers. So this morning I'm going to talk about our project, research project, and that is called Design, Development, and Prototyping of Robotic Sprayer for Uniform Surface Thickness Applications. Robotic sprayer or automated sprayer, no? And of course, I'm Engineer Charlton SE now, the presenter for this project, representing the Lyceum of the Philippines University in Batangas. So our title, to reiterate, our title is Design and Development and Prototyping of Robotic Sprayer for Uniform Surface Thickness Applications. And actually, we are two authors here because we have done this in Ethiopia a few years ago. I'm Engineer Charlton SE now, and then my partner in Ethiopia is Engineer Ahmed Endris, the supervisor in Bishoftu Automotive Industry, Defense University College of Engineering is the university that is affiliated in Bishoftu, Ethiopia. No? So let me read first the abstract. This project is conceived to address the requirements of uniform painting thickness problem in the bus body painting process of Bishoftu Automotive Industry Corporation. At present, all the painting activities are done manually, which results to inconsistent quality of paint surface thickness to bus panels. The manual painting also takes much longer time, meaning less productive, and poses health hazards to the operators, like the paint and fumes. Not to mention the physical fatigue incurred by the laborers when doing the painting processes the whole day. The robotic sprayer was developed using mechanical engineering and mechatronic disciplines with automation and simulation softwares that are commercially available. The machine incorporates a geared motor for rotating the lead screw that transports the spray gun holder mounted on the nut and carriage platform. The pneumatic cylinder actuates the spray gun trigger, and a number of sensors are located at a specified part of the machine for defining the limits of travel or the motion of the system, and to transfer the other parts of the bus to facilitate other painting operations. Same controller responsible for controlling the flow rate of paint coming from the spray gun by controlling the exact distance of the lever, which is actuated automatically by a small piston operated by a 3-way single solenoid directional control valve. All these discrete devices are controlled by a programmable logic controller, the Siemens Logo 12/24RC, or relay contact relay control. The relay ladder logic diagram and functional block diagram was meticulously designed and was used in programming the PLC using Siemens Logo software TIA, or Total Integrated Automation. The machine further includes a frame where the painting component carriage is mounted and driven by a geared motor. In this project, critical factors such as mechanical and structural loads were considered to design calculations. The system components, parts, and the assemblies were modeled analytically before the actual production. The modeling and production drawings were accompanied or accomplished through CATIA version 5, release 19, and ANSYS Mechanical APDL software package. The new spray paint were compared to that of manual painting system to see the effectiveness and quality of paint by analyzing the uh, uh, speed of spray gun motion and by measuring coating thickness painted on the surface of the bus. From the comparative analysis between the manual and automated painting process, 36.84 of uniformity of paint improvements from the existing system was achieved, and 62% of labor or manpower participation was completely reduced. Therefore, the newly designed machine is highly recommended to replace the existing manual painting system. And we have these keywords: coating thickness, degrees of freedom, PLC or programmable logic controller, Siemens Logo 12/24RC, three two-way single solenoid valve, and the lead screw carriage. Okay, so background of the study and statement of the problem. So the background is this. Now, the study was conducted in Ethiopia, where I serve as a professor in a military university, one of the biggest and most complete university in laboratory in East Africa. So uh, we had this partner corporation, Bishoftu Automotive Industry, and it is located in Bishoftu, Ethiopia, somewhere in 2017, 2018, that year, no, where there is a surge of rejects of painted bus panel in that mentioned year or period. So just a brief background of Bishoftu Automotive Engineering Industry. It is an Ethiopian manufacturing and assembly center for heavy armaments, tanks, and military vehicles. It is one of the organizations of the Ethiopian defense industry supporting the Ethiopian National Defense Force. Because when I was in Ethiopia, the university I was serving is under the Ethiopian National Defense Force or under the military. No? So that's why the military school and the industry or corporations are in partner and they are working hand in hand. No? So Bishoftu Automotive Engineering Incorporated is situated in a very large area in that city, and there are five departments, and they are as follows. No, tanks and armored vehicles manufacturing, rebuild of all tanks and armored vehicles used by Ethiopian forces. The military vehicles manufacturing, where there is a mechanical workshop, there are manufacturing departments for engines, and they are producing spare parts for tanks and armored vehicles also. Medium and heavy weapons manufacturing and electroplating section. So they have that department. Communications apparatus manufacturing and maintenance section. Repair and maintain various communications apparatus and electronic equipment in use with the Ethiopian forces. So here, as you can see, there's a motor manufacturing and mechanical workshop. So they are also manufacturing civilian buses and cars. Now, aside from military services and military transport engines and trucks and cars that are used by Ethiopian defense forces. So this is Ethiopia, the map of Ethiopia, to give you a brief background. So here is the capital, Addis Ababa, and somewhere 45 kilometer down, not west, is Bishoftu. So this is where the Bishoftu Automotive Engineering is located, and also the university that I'm working for. So here are the buses for the that are being manufactured in that corporation. So here are the buses, single, and this one, no, it's like a double bus horizontally. Excuse me. So here are the buses, and here is the plant. So one time there is this the famous president from Rwanda, President Paul Kagame, visits Bishop the automotive uh, industry. No? He is there, and statement of the problem. So, what are the problems that are needed to be addressed by this project? There is an inconsistent quality of paint distribution to bus panels. No, so some are thicker, some are thinner, some are rough, and some are smooth. So there's also the manual painting also takes much longer time, meaning the productivity is less, and it poses hazard to the operator. No? So the longer you are exposed to fumes from the painting um, spray, paint spray, no, it's dangerous to the health. Not to mention the physical fatigue when doing the painting for a longer period of time within the day. This process basically possesses redundancy of painting process, uses of operators inefficiently, inconsistent thickness of paint, and possesses ergonomic and safety issues to the operator. This project would like to address the issue of quality, efficiency, and safety by designing automated spray painting system. So our objectives, we have two, the general one and the other is specific objectives. The general objective is to design and develop and fabricate or prototype an automated painting or robotic painting system or a machine for bus body panels to achieve an efficient and good quality painting operation in Bischoff the automotive engineering industry. So the specific objectives are number one, to design and fabricate the lead screw mechanisms platform for X and Y motion or the horizontal vertical motion of automated painting system to attain an acceptable or equal distribution of paint throughout the body or of bus or bus panel. Number three, to design and develop PLC program or codes suited for the automated painting system and to perform a real-time validation of automated spraying system efficiency as against the manual operation. So those are our objectives. So scope and limitation, the project covers only a translational or straight rectilinear motion of a spray gun and in 2 degrees of freedom, meaning X and Y only. The Z-axis was not included in the study. Also, the movement uh, is in Cartesian plane of 2 axes only. No cylindrical or spherical motion included in this study. And we have this delimitation, the project's limitations in terms of resources, which explains why a scaled down prototype model, like it was 1 is to 10, was rather produced the rather than the actual dimension. So we go now to the methodology. So our methodology is divided into five sections, and that is one, data collection. Number two, concept design and selection. Number three is mechanical design. Number four is automation and controls, and number five, manufacturing of prototype. Yeah. So that is how we approach our approach for the study as a whole. No, and then of course there's a validation and testing at the end. So here is the bus that we use in the study. We visited the corporation and we were able to coordinate with the officials there. No? So lucky enough, during that time there was this painting of the bus. Now I think at this point of time it is still in the primer. Now they are coating primer on the bus, and this is the same bus that we were able to use during the study. So it is supplied, the body is supplied by Yutong, I think from China, and it has a dimension of 11.4545 meter in length, 2.5 meter in width, and 3.56 meter in height. Now there are 8 employees participating in the painting section for finishing one bus with 8 hours interval. So within the 8 hours, there are 8 employees that um, are working together, no, for this one bus. So the amount of paint for the completion of one bus needed is a total of 14 liters. Now 14 liters the volume, 8 liter normal paint. The composition is 8 liter paint. Then there's a hardener that is amounting to 4 liters and 2 liters thinner. And distance of nozzle tip of spray gun to bus is zero point 0.2 meters or 1, 2, 3. How much that's it's like 200 millimeter, right? So 20 centimeter. So here is 20 centimeter or 200 200 millimeters. So let me get 200 millimeter, right? Yeah. For obtaining a good quality of paint. Now, from such type of paint mixture, the following coating thickness was taken by considering 8 points on painted bus body shown below as a sample when one round of paint is performed using an instrument called micron. Okay, so there was this 8 points. Now, for example, there's a panel. Yeah, so there's a panel of our bus body panel. So there was this 8 points, no, and you have to get measurement from these 8 points to get the thickness, and below or the example of the results of the thickness being gathered. Now, uh, the spray gun that we use for the automated is the same as that of the manual, and here you can see it's like an inverted it's in a flip or inverted way. What we did here is we measured the so-called canopy, meaning the um, the measurement, no, the distance from the bus body up to here, no, as mentioned, is 20 centimeter, and also when you put the spray, no, when you put the spray gun, so it will have only a this one, right? It will have only so it will have only 20, no? So here is also 20 centimeter, right? So 20 centimeter in length, or 200 millimeter, no? So we use this data, no, for the incorporation in our automated spray. So it says here from 15 to 20 centimeter, depending on the pressure, no, from the compressor, of course. So it's 15 to 20 centimeter. So we could say that it is like if you're going to put that in a tolerance form, so it's like 17, no, nominal 17.5 plus or minus 2.5, right? So that is the the coverage of the spray, right? So we go now to the concept development. Now, how do we design the automatic spray painting system? There is a concept development phase that we follow, because we are following, and we have this subject of product development and design, and I was also the professor in product design and development. So we started the concept, no, up to the course of development. So there should be a problem or a statement, no, or something that needs to be improved. Then we have to identify the customer's needs. Now, in this case, that is the Bishop the Automotive Engineering Corporation. They need to have consistent thickness of coating in the established target specification. We have to establish the target, the thickness. Now, there's a specification in terms of thickness. Generate product concepts, meaning the concept alternatives or design. We will discuss that later on. Sales product concepts, I think it's optional. It's not more. Select product concepts. We have to select the product concept or the design concept. No, 3 to 5. So we introduce, we generate 3 products, as I'm going to explain later on. Then the product test, we test the product concept, or at least evaluate. Then we can set the final specifications, and then plan the downstream development. Now, as you go to the manufacturing, right? So this is just for concept development, right? So now, um, how did we establish the target specification? So our target specification is established based on the machine that is going to be designed and manufactured, or to undergo prototyping with with the following criteria. So we lay down the criteria as to 1 up to 10 based on the needs, and then we are going to evaluate it like a grading, no? Like a grading exercise from some standards, no? Like 5 is the most important, right? Now 5 is excellent, 4 is good, 3 is medium, and 2 for low, no, or 1, right? So if I may invite your attention here, no. So here is our grading. It should be consistent. 5, 4, 3, 2, and 1. So going back here, um, obtain the uniform point of distribution. Of course, that's very important, very critical, and very it's paramount to the study. Increased rate of painting, so not so much with the uniform distribution, so we graded that as 4. Allow large area of coverage of painted spray. It's also important, but not that much, so we make it 4. Paint spray gun distance to the bus body, it's 5 now. The distance is very important and can be maintained with readily available materials. Now, it's also very highly important. Ease of manufacturing, no, is 4. Noise and the compactness of size, more on ergonomics and or aesthetics or physical attributes. No, so it's 4. Efficiency, it should be efficient 4. Minimize labor participation, 3, because whether we have other people, the important thing is the distribution, no, and the uniform distribution, no? So we made it 3, and low material cost is 4. By the way, the importance was graded by a committee, no, by a group from us, from researchers, and from the designers, and also from the customers, the Bishop of the automotive engineering, no. So concept selection for drive mechanism. Actually, this whole exercise is called the Pew. There was this person from Ireland, no? Pew concept Pew concept selection method, right? So Pew concept selection method, that is the standard method for product design and development. Pew concept, now selection method. Now Pew. It is called. It is pronounced as Pew. Pew. Now, we have to select the drive mechanism, and we were able to generate 3 concepts, no? And these 3 concepts are for drive mechanism. They are as follows. Number 1 is A, which is this one, lead screw. The other is rack and pinion, meaning gear, and the other is like a fluid actuator, which is hydraulic. So to give you visual or an image of what we're talking about here. This one is the mechanism for lead screw. No? So where is the lead screw here? So as you can see, no, here is this, right? And this one, the dark area. So it's a lead screw. It's always used in machine tool building and the machine shop. No, there's a screw and the nut. No, there's a partner between the screw shaft and the nut. No, so the nut is traveling. The nut is traveling, and this one is the one that is fixed. No, it's just rotating. So the linear motion or translation is being affected by rotary because there's a DC motor. DC motor somewhere here. and another diesel motor is somewhere there. So when the motor rotates and it is coupled, mounted, no, in we mounted with a lead screw, it will produce a rotating, but at the same time, it can produce a linear, no, or translation due to knot, because the knot is the one traveling, no, so the one that is traveling. So let me put another color, no. So this is the concept number one, and in this portion, it's just the stand, no? Because we need to have a stand, no? And we are not yet complete. We are planning in the future to have a wheel, no, and automate the wheel. For now, for the sake of academic requirement and academic presentation in research, we just put the C channel here, no, as the foot, no, or the peg for the project. So here is a round shaft as a guide. No, this is the guide, and there's the bearing block. Roller guide weight is a roller guide way. No, circular rod, and they are made of steel frame. No? So this is the carriage. No, you are going to put the carriage in. So what is important here is the vertical, right? The vertical carriage and also the horizontal carriage to be affected by this lead screw, and the vertical by this lead screw. So it's just up and down, and then right to left. Okay. Now the second concept was with the use of gear and rock, no, rock and pinion. No, so this is the pinion, no, in mechanical engineering term, and this is the straight rock, no, like a guide for the spar gear for the pinion, right? So this is the so-called rock, yeah, okay. And this is the carriage where you're gonna put the mechanism like the paint and so on, no? So this is another, right? And also, I think our last is hydraulic cylinder drive mechanism for spray painting. No, so we also thought of fluid power actuators. So basically, it's a cylinder like that. No, so there's a cylinder and there's a piston, and this is the rod. Okay, so in order for you to visualize, if I'm gonna make it in 3D, no, so it's like a cylinder, meaning there's an area, circular area, and the length, no, so that's a cylinder, the geometric basic figure. But inside there's a plate or a disc, no, it's called piston, and what is mounted in the center, the center of the piston is the rod, piston rod, and this is the piston plate, right? Piston plate. Okay, no. So what it's going to do is if there's a fluid, no, inlet, when the fluid enters, whether air, if it's pneumatic, but in this case it is hydraulic oil because it's hydraulic, meaning it's liquid. Then this piston, plunger, or plate will go up now because the fluid will come here, right? So let me correct the drawing. So if the piston comes here, it will be filled with fluid, pressurized fluid. So if there's a pressurized fluid and you have an area that is circular, right? So you have an area, you will develop a force, right? From the elementary definition, pressure is force over area. That's why the force will push it upward. Or when you utilize this, another port, it will push the piston rod downward. No? So that's why it is double acting cylinder. No? So this port A, this the port B. Okay. So we will, of course, we will put the spray gun here, no, at the tip of the plunger or the rod. Now, this is the rod, right? This is the rod. Yeah. So we will put the spray so that once the cylinder is going upward, so it can spray, right? So which among the three are we going to use? There is some systematic method for evaluating and deliberating this. Now, so that is called Pew selection method, if I may write it again now. So Pew, Stuart Pew from Ireland. So what you're gonna do is you select the criteria here: ease of manufacturing, speed, ease of maintenance, noise, lubrication, cost, and efficiency. These are the criteria that we used also a while ago, right? It is, I mean, somehow related, now efficiency, noise, and others. So those are the these are the selected criteria from among the chosen criteria. So we just sorted out, no, the most important criteria, and we're going to put weight, no, because it's this pew selection method is the selection by importance, no. So you're gonna assign how much weight is manufacturing, no? 25%. How much weight or importance the speed is 15%. Ease of maintenance is 10. Noise is 10. We don't want to have a noisy spray, of course, because the compressor is already noisy. Then the lubrication use, the cost is also important. It is 15, and then this is 20. So when you total this, when you add all this, it should have 100%. Now, the rating from our initial exercise. Now, for example, if I may get this, ease of manufacturing. Uh, yeah, here, right? Ease of manufacturing and others. So you will have a rating also from the group, no, from the design design people, the design committee, and all the stakeholders like the users, no, and the officers, the decision makers, and so on. So we put here rating is 5, 4, 5, 4, 5, 4. Okay, then all you have to do is to get the weighted score, and that is going to be point 2, then it's this point 27, this point 5. You just have to multiply the two values, point 5, then point 4, and then this one point 33, and point 2. So that's weighted, and then you go to the next, which is the rack and pinion. So you have to give I score 2, no, because it's more difficult, no, and then speed is 2, no, this one is 4, meaning higher. This is higher, can yield a higher speed, no, of travel, rather compared to the gear. And then here, if you're gonna compare, they are equal, right? And this is 5 lubrication. You need to have good lubrication. This one is 3, and then cost 5, a bit higher. This one is 4, and this one is 4 and 4. This one, the lead screw is of the advantage. So because here is 2 only and 2 only. So all you have to do is to again, no, get the weighted score for this. Now, so all you have to do is to get the weighted score. You get the total, and then you divide each item. So like here, no, so you get the score. You can get this when you get the total, and then you divide by the from the individual now. So also here, the rating is 3, 3, and then 5. Why is it 5? Speed, because cylinder, you can have good speed if you have a very good valve or the tank, right? And then the ease of maintenance, it's hard to maintain the hydraulic. It's hard because the tank and the pressurized fluid will yield some leakage in the long run, and the heat of the fluid. So the oil tank will be heated, and you can only manage that if you will put another device that is a cooler, oil cooler, and that's another investment. No, so those are the things. Lubrication, three, and then cost, three, and then efficiency is five, right? No, so and then all you have to do is to add all the weighted score. No, so weighted, you just add, then you will get 2.3, then 2.03, then this one is 2.9. No, so by the numerical score, you can rank according to Pew, no, Pew selection method, no, which is the drive mechanism that you intend to continue, no, because of this evaluation. So here is the lowest, 2.03, the rack and pinion. Here is the second, and this is the first, right? So here, yes, are we going to continue to develop this? So we said yes. This one is no. This one is no. No, because this one has the highest rank. No, based on the weighted percentage, right? So we decided to continue with the concept one, which is using the lead screw. That's why we were able to come up with the lead screw. No, to further validate, the or to substantiate the evaluation, you can continue the pew selection method with evaluating or deliberating the merits. When I say merits, you can put plus now for its positive or meritable attributes. Now, for example, here, lead screw is of manufacturing. Of course, you're just going to machine it, right? Three, rack and pinion, meaning it's less, because you're going to manufacture the rack, you're going to manufacture the pinion. So that adds more complexity. Hydraulic, it's just difficult unless you order it now, but if you're going to build to per order, no, you have to build it based on a specification. That's gonna be more difficult because you're going to manufacture the cylinder and the piston, and then the seat, and then all the o-rings, and like a gasket, no, yung o-rings to prevent leakage, no. So speed, lead screw is highest, and it's more precise because of the pitch. No, rack in pinion is only two, and then hydraulic cylinder is only two. No, it depends on the pressure being given. Ease of maintenance, so two, they are all equal, I guess. Noise, two. Rack and pinion is high. Hydraulic is low because it's only fluid. It has less noise, right? So but the pump could have a noisy. Yeah? So that means it was rendered low, right? This is the legend. I almost forgot. So here, so low merit, right? So cost, right? So when you talk of cost, it is affordable. I mean high. No, this one is medium, and this is also high. Hydraulic cylinder. Efficiency, lead screw is efficient and it's precise. Then this one is not so much. And then here is also uh, more on precise. Lubrication use, lead screw, only this, no? This one, rack and pinion, it needs high because the frequent contact of pinion, the pinion gear and the rack, and hydraulic cylinder, it has always the lubrication component because it's using oil, and you need the lubrication in other parts. Compact size, I think they are all. equal. Okay, so these are the another way of selecting the or testing the concept, no? So what we decided here is the concept number one, no? Based on few selection method because of the merits, now that we were able to evaluate. And then here is the theoretical or technical model framework. What we have here is this dynamic model of the whole system. It's more on the dynamic or movement, no? Types of cylinder, you need to know the type of screw, fatigue of guideway, length of flexibility or the precision of length of screw. Then here, the type of cylinder or actuator, nozzle, diameter, spray performance model of spray painting, speed paint, precision of coating. That's the result. Meaning this is in the spray gun, no, in the trigger. This one is in the guideway, right? Then this one, performance of model or carriage, type of material, then the speed motor, the geometry is are the inputs, and the portability, weight of carriage. So these are the metrics. No? Since this is the model, the inputs, and these are the model for the outputs, the metrics. Because how do we evaluate? We can evaluate through metrics. No, is it portable? Is it lightweight? No, weight of the carriage, right? This one is speed of the paint, I mean paint gun, then precision of coating, right? Here is the length of flexibility and precision length of screw. So you just have to know and design the type of screw and the type of the shaft or the cylinder. Okay, so here design of mechanical elements and automation design for spray painting mechanism because we already decided for the lead screw mechanism. So here is the design. We have to have a bearing pillow block here, no? So the seat where the seat of the shaft, no? So it has a bearing, but the shaft will go in the center or the middle, and then this is the lead screw, no? The specifications were able to design and get the pitch and the other, no? The number of entry, or is it right hand or left hand? Then we just put the spray gun here, no? So this here is a spray gun. It is mounted here. That's why it can go, no, upward and downward because it is mounted on the nut. Okay, nut. NUT. Okay. So that is the whole mechanism, isometric view of the carriage with accessories. No? So the carriage is this as a whole. So it is carrying different components, the spray gun, and then the pillow block of with the bearing, and also the lead screw. Okay. So what we did here is we identified the materials, and then the projected amount of material we were able to identify, and then we calculate the weight, no? So how did we calculate the weight? We cut the material. So we cut the material. We have a shop there in the university. So for example, sheet metal. So we cut this. So length, width, and then there's a thickness. Okay. So very easy, very practical way is to use weighing scale. So we scale, we put them into weighing scale, then we're able to measure each weight, no? So 9 kilogram, including the PLC and the electronics. This one is 8 kilogram, and so on and so forth, right? So all in all, the total mass of this carriage mechanism and its accessories is roughly 41 kilogram. And why do we need to know the weight? We need to know the weight of this mechanism because we have to manufacture a structure that will or that can withstand the load, that will carry this, that can carry this. Now we have to have a structure, a metal structure that can carry this, right? For example, the platform or the table, no, because this is the load, no. So from that load, we should be able to know the dimensions of the platform, because the platform will be the one who will accommodate all this mechanism. No? So that's the principle. Why do we get? Why? How did we get the different weights? No, or the total load weight. Okay. Now, the following will be the mechanical part, which is the design. And I don't have to elaborate this though, because it's not a full lecture. It is just a presentation. So what we did are the series of design for the major components. For example, the lead screw. This is our criteria. It should be strong, it should be highly machinable, and so on and so on. We could do the following. We could test the strength. We could draw the bending diagram and the shear diagram and so on and so forth, just to design a lead screw. So it's a lot. It's a really hard work, full hard work. Now I just get the excerpt from the full paper. Now the paper is submitted in the to the panel now and to the organizing committee now. But I just put some to show that we really had very serious work done with respect to mechanical design, no, because we are both mechanical engineers. We help each other now in the calculation. So this is the shear and moment diagram. Now, so vertical shear, and this is the moment diagram, to know which part of the system will incur a very high load, no, and what kind of load, no. So normally it's it's just a weight load, no. So this the concentration of weight, and then this the shear diagram and the moment diagram. So also, as I told you, I'm not going to discuss the calculations because it's a lot. It is comprising half of the project work, the project documentation. So what I'm gonna do is just to reiterate, no, and maybe I'll just focus on the automation or the robotic part. How did I do the program? How did I do the automation? Because this is standard, no? It's mechanical. So the design of nut, how do we select the motor, the torque, no? At what kind of rating, and what kind of service, no? So it's all there. No, I just capture, I just screenshot the part so that to show you that there's a lot of serious and tedious mechanical design work being put into this project study. We also designed the keyway, no? So there's a shaft for those who are not mechanical engineer, no? So there's a shaft, no, a solid shaft. Then once you are going to couple some another part, no, so you have to machine this, right? And this is the key, and this portion is keyway. So if you redraw the shaft, sorry for my drawing, but here is the shaft now, no? Yeah, cutaway view. So meaning this is the cut portion of this, no? So you're gonna insert that, no, the key, you're gonna insert in the keyway. So we designed the keyway, because there's a design there for, you know dimension, no. There's the breadth, width, and the height, yeah. And then you will have to experience some um, forces or stress like shearing, no, and bearing, yeah. So shearing and bearing will affect the keyway. So here is the formula. I'm not going to discuss this due to time constraints, no. So here, once we design the key, so you will have the width and the height, and then the length, no? So these are the important in the key design: width, height, and the length, and then depending on the shaft diameter. I think we have the 33, 35 millimeter diameter, no, in that lead screw. So it's you have to just choose if your diameter, shaft diameter, is falling within this range. Then you just have to get this following dimensions of the key. Now 8 by 8, then you just have to get this. Now within 32 to 133, it's a long range not to choose from. Yeah. So we also designed the bearing. No. So these are symbol for the bearing, and then normally the load is always at the middle, and you can design the bearing with the following formula. And also there's a formula for the bearing. Yeah. So we use the SKF. It's a commercial. So every bearing has also their own standards and formulas. So we follow the formulas for the SKF design, so that we could arrive with the correct diameter, and also the bearing life. No. Yeah. So here is the continuation of the bearing, now thrust bearing. Then we were able to select the frame of for the supporting system, because we are going to get the to carry the carriage or hold the carriage. So we just need a table, no, for the meantime, to utilize, so that all these things here can be accommodated. So we need to have a kind of platform, no? And then we just have to calculate the slenderness ratio, no, with all this formula, right? We are going to use column formula. So the column load, or the column bending, no, load. So I just got it from the document. So I just extract it, so that you can see how much mechanical activities have we put into this project. So welding, because a lot of these structures we are going to weld. So we're going to weld that, we're going to weld this and the other. So we have a particular section for welding, and also the painting system and component. Now this is the common painting system. To replace the use of hand, we just use the cylinder, right? The pneumatic cylinder, so that when we trigger the cylinder, it will go retracted. No? So it will go there, retract. When it retract, then it will have this nozzle tip open, and then it will spurt. No, it will throw the mixed paint, no, intended for the bus panel. Now that is what we're done. So we were able to design the pneumatic cylinder. So the design of the pneumatic cylinder is very easy. Just need to know the this diameter. So how to you calculate the diameter? So it's there, right? So it has to do with the pressure, force over area, no? So you could know the the dimension, because you have the pressure and the force developed, you know, because you have the area. Now you will know the area now, because pressure times area is the force. If you know the force that needs to actuate this trigger, right? So the trigger of this gun, no, you need how much force. Now we already calculated. So we need the force here, and then we have the pressure. We can get the area, right? So pressure, force over area. The pressure is coming from the compressor, and the force is we already calculated how much force is needed to actuate this, no, this gun. And then you can get the area, and area is simply when you cross multiplies force over pressure, right? And of course, to expand or decompose this, pi d squared over 4, this is constant both. Then you can get the square diameter, you you can get the root of that. You extract the root, and you will have this diameter for the cylinder, which is 19.99. And of course, you know that in a practical, it is not available. Who will give you 19.99? Nobody. So the next higher is 20 millimeter. Now, so based on design, we have to use 20 millimeter diameter. So those are the mechanical works that we have done, no? The serious mechanical design in order to put up a machine like this. Now, so here is this. Here is the motor, no, DC motor that will drive this lead screw. Here is the motor, another motor that will drive this, no, up and down. And this is the spray gun. And there's a cylinder here that will trigger the handle, right? So these are just the guide for the carriage so that it can move like X, no, and positive and X negative, and here now on this side, yeah, vertical, no, positive and negative, right? Yeah, so this is the project or the prototype that we did, no, but the video and other pictures are left in Ethiopia. I wasn't able to get. No? So we'll just access it when I contacted our research partner, Engineer Ahmed Endris. So now we will go to the automation part. We finished with the mechanical because we've also, before that, we finished with the concept development. How did we choose the concept? Then we finished the mechanical design. Now I want to focus on the automation part. No, so we will discuss this thoroughly. So now we are in the automation system, the automation part. No, what makes it automated? So this is the wiring diagram for the automated bus body spray painting system to both motors and solenoid. No, so I'll try my best to explain this so that the audience could understand. Um, so let me have this here, right? So normally the control of any system is composed of the two parts of a circuit. No, so one is control control circuit, and the other is power circuit. Circuit is where the relays and the sensors and the other switches are mounted, and the other circuit is power, which I think I put here at the bottom because of the constraints in space. No? So I think here, yeah, here's the power circuit. No? So the power circuit consists of the power devices, which is this one. In this case, we only have the two motors, right? The two motors. Let me put here, right, so that everybody will understand. The motor one for vertical, right? No, movement or motion. No, so motor one, right? And then the other is motor 2, which is for the horizontal. No, so basically what I'm saying is the the carriage will go up, and that is because of the motor, right? Because of the motor that is attached here. Yeah, so it will turn the lead screw, and the lead screw has the nut, and the nut is where the carriage is mounted. Now, so here's the motor, here is the nut. So the once the lead screw is rotating, now is perennially rotating. So this is the nut, and in that nut, the carriage is sitting upon, right? So this can travel up and down because the DC motor that we have is counterclockwise, meaning by. now bidirectional, meaning it can move clockwise and counterclockwise. So that's the part of motor one here, right? So as you can see here, now if I make it right, so this is motor one, now up. Where is our, yeah, here? So here is motor one up, here is down, right? Here is down, and this one is right, going to the right. Now, so this circuit basically simulates the cycle, not the cycle, one cycle that we use. Now we did not intend to paint the whole bus and showing all the circuits now, because it's gonna be lengthy. It could be very tedious. So we pick up like a one cycle. The motor will go up as it sprays. No, it is spraying while it is moving up. Now, for example, this is the spray gun. Yeah, here is the triggering is the cylinder, right? So once the cylinder uh, goes retracted, yeah, once it retracts, it will trigger the triggering handle. Then it will give uh, spray, no. But this one should go up, no, I mean this carriage should go up. It's going up so that it can um, spray here on the vertical, right? So that's the essence of the motor one, and the motor one up, right? And this one motor one down. When it goes down, this one is going to the rightward, right? So now let me give justification to this circuit, so that all of us could learn, no? So look at this, no? So we could say that this is the bus bar, that is line 1 and line 2. And when we're talking of control system, we are dealing with the low voltage. So what we use there, because it's controlled by PLC, 24 volts DC. And this is just representation of the relay ladder logic that we implemented. Actually, we don't have the actual relay, because the relay is inside the PLC. It's here, right? So these are the internal relays that I use in programming the Siemens, no? But just to show you the principle, no, from the actual relay, I can show you the sequence. So we need a start. No, the standard is we need a start and stop, and it's being represented by these two devices. So here, start and stop. So all we have to do is to press this start in this momentary push button, or the so-called mushroom. So if that is the case, the power will come here now. So as you can see, I'm putting some kind of lines now, because we already made a contact in start. And the stop is normally closed, so the power can go here, right? And then the relay 6 contact is normally closed, so the electricity or the power can go here, energizing R1, no? So when the R1 is energized, no, the coil is energized, all the contacts will be affected. So we're gonna look for all the R1, R sub 1, no? So it will be closed, right? It will be closed, so this one will be closed, no? But since this one is not yet, no, it is not triggering the S1, so nothing is happening now. So look at this, at the power. What is R1 responsible for? Let's look at this. As you can see, there are two motion that the R1 could be responsible for. Now, when it gets close and this one gets close, motor up, meaning if we put clockwise now, because it is powered by relay now. It is powered by relay or contactor. I use a relay. I think there are eight contacts now. So when it's powered by relay or contactor, so once the contact is being closed here, so let me use another. The electricity from line 1 to line 2 no, will be active. So from the line one, look at this, yeah. So the electricity will travel like this, and this is already closed because of the R1 contact, yeah. So the electricity will flow, and this is also closed, no, so it can just pass through. So energizing the DC motor, no. So this is the DC motor. It will energize. So what will happen is this, no, the motor will go up because it is powered. But at the same time, if you will see here, no, so another electricity flow will come because R1 is there, so it is normally closed, normally closed, normally closed. So it can go here, and this is also R2, this is also normally closed. It can pass through, and then energizing the solenoid. Why solenoid? Here, because this one is powered by solenoid, no, because solenoid is just an electromagnet that can affect a motion, no, there's a force, so that force will tend to make the solenoid switch over, no, so the valve, I mean, so this is the solenoid, and this is the spring, so it will switch over. So from here, no, so from here, three-two-way. Now this is three-two-way valve going to the atmosphere, and then this one is going up. So it will switch over before it is here, then it will come here. So it will give a pressure here. No, if it gives a pressure here, because we reverse the mounting of the hose or the polyurethane, so it will go retract. No, so from forward, it will retract. No, then it will pull pull the trigger. When you pull the trigger, then it will spurt some uh, pink, no, while the motor is here. No, the motor is here, so the carriage, the whole carriage, no, it is driving the the so-called lead screw, and then this is going up. So while it's going up, no, here, no, while it's going up here, then it is painting the bus body. Now, because this is the bus body, right? So this the carriage where it handles, it carries the spray gun, right? So that's why in the control circuit there's this description of motor one up, meaning the motor one is responsible for the vertical here. The motor one is responsible for the vertical, and then the solenoid valve is on. So when it's on, it will pull. It will pull the trigger, and it will spray, So that's it. And then we put some sensors like electromechanical switch or the inductive and capacitive sensors. So and they are represented by S1. Look at this now. Look at this. Once the carriage reach the limit in vertical, now it will go up like a 40. Now we designed it like 40 centimeter, and the horizontal is 20 centimeter. When it goes up, there's a sensor here, right? There's a sensor here. It will just define the limit. No, we have sensor here and we have sensor at the bottom. So we define the vertical distance where the lead screw could only travel. So once it reached the limit in the upward direction, so let me put here. Look at this. This will close, no, right? So this switch or sensor will close. And once this is closed, so the electricity can travel here, right? It will travel here. I'm just putting a kind of shading so that you will see. But R1 is closed already, no, because of this, right? R1. So it will go to R2, right? So all the R2 will be affected. So this will have a latch, no, or logic or latch. It is called latch, even though the sensor is being open, it's still already latched. So the power or the current can also come here at the parallel. No, how did you see it's parallel? This one, right? This one is parallel to this. This one is parallel to this. No, parallel. So that parallel is or logic in PLC, right? So look at this. We just finished this. So R2 R2 is responsible for what? I think there are three. Motor 2 is up, meaning is activated. Now motor is this motor 2? Now motor 2 is up, so it will go that way. Then solenoid valve off because you already have painted up to the top. So you just have to stop the solenoid valve to stop the paint gun, no? So you have to off the gun and then M2 to the right, no? So here M2 to the right. So the motor should travel to the right, no? So the motor should travel to the right. Okay? So it goes to the right. Okay? Now, how did we see that? Now, there are three. Motor 1 up, solenoid valve off, and then M2 right on. So you go to the power circuit. How is that happening here? So here, no, if you're gonna see this, no, this one, motor 2 right, no, look at this, motor 2 right, di ba? So this one is motor 2 right. How did it happen? Because of energizing the relay 2. So you look at all the relay 2, this one, no, R2 is close, and then here R2. So look at the R2. Look at this R2. Yeah, R2. So the electricity will come here. Let me shade it like this. Yeah, R2. This one is already closed. So it will energize the motor, the responsible going right, no? So here in the horizontal motion. Yeah, here. So if this vertical, the motor is here. Here is the going to the right, no? Because this one is right, left, up, down. No? So here is the concerned motor that we are talking about right now because it's going to the right side. No, it's going to the right side. No, so that can be reflected here in this circuit. No, so R2 will energize the motor because this is already normally closed. Then it will energize the motor. What else? Can you see another R2 somewhere? No, so R2. What about this? No, so here R2 solenoid normally close, it will open, no, because once the R2 is activated, it will open. Okay, so if I put that in the original, yeah, look at this. No, so R2, look at this. What I want to emphasize is this, right? The motor 1, when R2 is activated, look at this, when R2 is activated, no, the electricity will flow here, it will go here, and then go here to activate M2, no, the motor to the right. Once it's moving to the right, what's happening to other R2? This will stop, no, so this is normally uh, close, R2, it will open, right? From normally close, it becomes normally open. So it will, yeah, if that is the R2, it will open, yeah. So if this the R2, it will become an R2 of normally open, yeah. So motor 1 will stop, and also this will be cut, it will become open, solenoid valve will stop. Why should it stop? Because you're finishing the vertical, right? So once you reach the limit, it will the limit switch. It will give signal to R2. No, as you can see here. Look at this. No, so the sensor there will give signal to R2. So the R2 now, if you can see, once it's energized, the coil, the contacts will be affected. So it becomes open. So this open motor 1 that is going upward will stop, and R2, the solenoid, right? It's normally closed. It will become open, so it will also stop from painting. Now, because it is pulling the trigger. Now, it is going forward again. Now that is how we design it. Another is this R2. Once it is off, this one will become on, right? The current can travel now here. What does it do? It will pass here in R3, then it will energize the motor that is responsible for going to the right, no, rightward. No. Okay? So if I may summarize, this will stop, upward will stop, the paint will stop, and then this one will go to the right. So if I may illustrate this, so coming from here, now this one is our dimension, that is 40 centimeter, and this one is 20 centimeter. So once it reach here, there's a sensor, right? Sensor here in the person of S1. So we put the sensor as S1. So what will happen right now is this is S1. So the S1 will give signal to R2, and then the R2 coil will affect the contact. So this will become open. The motor will stop here, no? So because it's open. And then this is open. The solenoid will stop to paint. Now from here, it's painting, it's painting, it's painting. Then it will reach the topmost because of this, no, and then the solenoid will stop because this will become open, the R2. And what is the other duty of the R2? You should be able to find out because you have the diagram. So R2 is also responsible, no, it will pass RT, motor 2 rightward, meaning here. So your motor 2, this motor 1, right? Motor 1, right? Going up. Motor 2 is going to the right. Okay? So this is rightward, meaning the X. This is motor 1, the Y. Okay? So it will only travel 20 centimeter of a distance, no? And the vertical is 40 centimeter. Now, once it reaches this, it will travel 20 centimeters so that it can position very well. Now, what is the logic here? The logic here is you can paint downward. No? When you open the paint, you can open the paint gun, no, downward. So it will spray from top to bottom. And then also the vertical, which is M1, going down, right? So at this one, here, M2, sorry. No? So this one is going down. No? So you can have the go down. So this one is going down. It will paint, no? It will paint from the top, top, middle, then bottom as it goes down. So that's why it will be activated by what? By R3. No? So how did you know R3? You go back there. There's something that triggers the R3, and that is S2. And where is the S2 located? No, it's located here at the 20 centimeter vertical. No? So once it's here, no, there's a sensor here. Once it trigger, then the going down will be affected, no, because there's a sensor here. What sensor is this? Sensor 2. So go back to the control circuit, find the sensor 2 here. Look at this, the sensor 2, it will go, the current will go here, then it will continue. This already normally closed because of this, no, to activate R3. So the R3 will be energized, and that is R3 is responsible for M2 right, meaning M2, the motor going to right, and M1 going down. I told you it is on the top. First, it will go to the right because it wants a 20 centimeter, no, canopy distance, because that's the width of the spray gun, no? The canopy or the area that it can encompass is 20 centimeters. So the motor will go here in the X. Then now you can go down. Now, so the motor 1 again will go down. So That's the responsibility of R3. No, R3. Look at this, R3. So all the R3 will be affected. This will become latch. This will become preset. And then look at this on the power. So find the R3 now. So the R3 now is this. No, it will trigger the motor down because it wants to paint downward because you already achieved the 20 centimeter uh, going rightward, not to give a distance so that it can spurt its canopy, no, its coverage of paint. So it will go 20 centimeter, and then there's this sensor. That sensor is S3 and S3 S2, I'm sorry, S2. So that is S2. It will give signal to R3. So R3, R3, look for R3 all over the place. So R3, R3 here, no, then the signal will come here, energizing R3. So once R3 is energized, the current can come here. This already closed R4, that's NC. So it will go down. The motor now can go down here. Look at this. The motor now can go down, right? So it is this 20. First it goes up, stop, then it goes rightward. The sensor will detect, and then it can go now downward. And that downward, the responsible motor is vertical, right? Yeah, here. Motor 1, down. Because a while ago it is up. Now it's down. So it will go down while the motor is on, no? Because the R4 is, or R3 is on, right? The R3 is on. So that's the case. Now, if you want to continue, now I'm just saying that it's just a sequence. Now, once it goes down, it will touch S3. Now, this one is S3. Once it is going down, it will touch the sensor 3. So once it touch, it will trigger. It will become normally closed. The current can pass because this is already closed due to this. No, then it will trigger R4. So what is R4? You can also see all the contacts in R4. Make it close for the preset, then try to find the R4 in the power circuit. So where is R4? R4 here is the R4, right? So this one, R3 is closed a while ago, no? And then R4 it will open, so it can go to the solenoid, right? It can go to the solenoid. Why should the solenoid be active again? Because you're going to paint again, right? Going down, there should be some painting process happening so that you can utilize the downward motion or force. That's why here there's an R3. No, it's triggering the solenoid again. Okay, and that is the sequence. So we were only left one, I guess. So let me tackle this. So once you have S3, it will give signal to this preset, and then it will energize R4. So once the R4 is energized, that R4 is responsible for here. No, it will open the going down. No, because it's going down, it will stop. It will open, right? Because it's normally closed, it will become normally open. Then the motor will stop, and we do not know where. No, so it should stop such that it should go to its destination. So any R4 that you can see, this one I think is this R4. It's kind of covered, right? Now, so this is R4. Look at this. Now, so this is a parallel. I would like you to look at this. So this is parallel, and this, no? So once it is closed, what happens this, right? The current can pass through. It can pass through also here, which is closed. Then it could bypass this, right? So here is the motor 2 rightward. Again, now motor 2 right. Now because it should go to the right side again, right? So here, so there's a sensor 4. You know, when you deal with the right, I mean the relay 4, then the sensor 4 will be closed. This will be closed, R4 R4. So if it's closed, then the power can now travel here, and here now energizing R5. So what's the responsibility of R5? Look at this. Is there R5 here? R4, R3? No, so that R5 is part of the circuit, right? So R5, then R5, it will preset. Then when it reaches another sensor, it will close, and then it will go to R6, which is reset. Reset means this one. Now this will become open. Now it's closed, it becomes open. So when it is open, so there's no power here, there's no latch, there's no preset, then there's no power here. Then no power here, no power here, and then this one is uh, going to be deactivated now, so all will be reset now in that particular case. So my point is it takes time to know. Now I take many years to study this circuit now, so uh, you can only understand if you grasp and absorb all this lecture on the relay control logic. It's a logic of ladder uh, form of bus in the circuit. Na? So we already take up this, no, the power circuit and the control circuit. We will go now to the PLC because I use PLC Siemens. No, I just show you this no manually so that I can show you what's happening or you can review. So this one is the actual Siemens logo. You can save that as PDF. That's why I was able to send the PDF or screenshot. No, so all this same thing. No, so normally open is just contact. No, normally open. This one is normally close, right? So normally close. So this one is output instead of circle or others. No, so it becomes close and open parenthesis, right, for the output. So here is for the actual power devices. Now it's like open and close, like this one. Yeah. So we have four outputs. No. So what I'm trying to convey is this. So the relay ladder logic in manual is converted to PLC because this one is inside the device, no? So I just use the logic for elementary electrical tracing and programming. Then you can program, you can use the sophisticated program using the simulation for the PLC Siemens. So this is the circuit for control, and this is the circuit for power. How do you know it's power? Because there's a power device. There's a motor. What else? There's a solenoid valve, right? So there's a motor and solenoid valve. So motor one, this one, no? So motor one is up. Then later on, this one is motor down, will go down, right? So this one is another motor. Yeah? So just have to follow this. Yeah. So this one is another solenoid and output. No, so this one is solenoid for triggering the paint, and this one is the output. This one now, and it could be monitor also. So here are the list of materials like a BOM, no, bill of materials. We have a table, and then there's the specifications, and these are the devices, and then these are the materials, no, and so on and so on, so forth. No, so here is the cost. No, we run down all the materials and then the expected cost for this. Okay, so now the next is significant findings or results of the study, and then we'll go now to the summary and the conclusion and the recommendation, and that's uh, is trying to finish the this discussion. So at this point of time, we're going to discuss the ladder logic diagram, which is being used by our controller, which is the Siemens. So here, I'm going to explain briefly what's happening. So the same thing with the ordinary relay ladder logic, which is found in the actual devices or discrete devices. This one is the same sequence could be followed, but the only difference is that these relays are represented now by M, letter M, M1, M2, M3, M4, M5, and M6. Now, same thing here. Look at this. R1, R2, R3, R4, R5, R6. So when you translate this into PLC, it will become M. No, that is the language used by the controller, which is the Siemens. No, as logo series. So here, if you press, no, this is line one, no, and then line two normally is not being put, no, but of course there's a line two somewhere here, no. Look at this, no. If I press I2, which is the address for the start, this will become close, and now the power can come here, and then this is the stop button. This is the start push button, so the power can continue, and this is the contact of M6, which is this. Now, so the contact of this is put here at the beginning before the relay coil of M1. So it will come here, it will energize this. So when M1 is energized, all the M1 will be affected. Look at this. So this will be closed. This will be closed. So the power can travel here, no? Even though I do not I'm no longer pressing the start push button, still the power is on because of this circuit connection, which is called latch. So we call this latch or hold holding relay contact, no? So it can still provide power to M1, and then M1, as long as this is energized, this will be closed, this will be closed, and try to find another M1 in the whole circuit, because this one is the control circuit and this one is the power circuit. So M1 is this, no, it will be closed. So the line 1 here, it will supply power continuously here. M2 is closed. Then here is will be energized. Now, so the one that we use here is Q2. No? Q2. The address that was given, the given that was given is Q2. No? So what is Q2 responsible for? Q2 is the M1. No? So this one is the equivalent in PLC here is Q2. That's motor 1. And we know that motor 1 is here, motor 1 up and solenoid valve on. So let us see that if that's really going to happen when we are using the power circuit, no? So let me erase this first. Oh, it's not erasing. So anyway, um, we'll just continue the the explanation. So we're gonna get the pen, and in this case I'm gonna use this blue, right? So this one is powering the Q2. The Q2 is responsible for motor 1 up, and then solenoid valve on. Yeah, so the motor will move up so that it can spray, no? So this is the spray. Because of the solenoid, it will trigger the gun, so it will spray while it is going up, so it is distributing paint evenly, right? When it reach the topmost, there's a sensor here, right? So we put a sensor, it's like inductive or capacitive, so that the portion of the metal, no, the metal will be detected, no? Inductive sensor can detect metal. So once it is detected, I mean the metal part is detected, then it will change its status, no, from normally open to normally closed, and that is our sensor, no. This one, our sensor is this one. It will become closed. So when it's closed, it will travel here, right? And this one is closed because of this. Then it will energize M2. No, that's the relay in charge for the M1 up off. So the motor that's going up will be off, and then the solenoid valve will be off, and the M2 motor 2 going to the right will be on. Now motor 2 rightward will be on. Now so there are three outputs that is being triggered by the M2. Now we'll see that in the power circuit. So look at this. This is already energized, these two. So look all at the M2. So let me first have this. The M2, once this is energized, this will be closed and this will be closed. So the power can also come here. Look at this, right? So this is the power. I'm having this line to exaggerate. Yeah. So it's still providing power to M2. Although you remove the sensor in I3, still it is powered because of the so-called latch or the holding contact, right? Holding contact. Okay. Now, so look at all the M2 for the whole circuit. So M2, look at this. We knew, according to our logic, that M2 relay 2 is responsible for stopping the motor that is going up, right? So this one will become open. So once it is open, the power is only up to here. Now, because already open, only up to here. So it cannot transcend, it cannot pass because the resistance is its maximum. You cannot pass here. No? So Q2 will be de-energized. So meaning the motor going up, this motor that is responsible for going up will be off, right? So here, this one will be off. And then look at the M2. So this one is closed before due to M1. So this one will be off now because it will be open. So that one a while ago, then it will be open, right? So this will become open. What is that? Look at this now, so that we will have a guide here now. So the solenoid valve, yeah. So the solenoid valve is closed before, then it becomes open. So naturally it will be off because the painting should stop, right? When it's going up, it is painting, 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 painting. Then there's a sensor here. No, it's already at the top, no? So nothing more. No, it should stop because that's the only canopy or the area that we are trying to be concerned about, and that is 20 centimeter by 40, right? 40 centimeter up. So when it reaches the 40 centimeter, it will sense by the sensor that will trigger the M2, and then the M2 will give signal to all those concerned, like this one. Look at this, right? The M2, no, it will be stopped. So it will become from normally closed, it will become normally open. So the Q2 here for the motor 1, no, because Q2 is the address that I use, it will stop. But here, it will also stop. No, the painting due to solenoid, the triggering was done by the solenoid. It will now become closed. No, because it will be in the forward position. It will become closed. So there's no more spray. No, spray is off at this case, right? Let's try to find another M2. So here, M2 will be closed. So the power can travel here, right? M2, M2. It will go to the M2, then M3 is closed, so it will energize Q3, which is responsible for the motor going to the right, right? So look at this now, because this is PLC and this is the relay, no? Is more complete. Look at it. So M3 is at this one, no? M2, no? When this is energized, M2 to the right will become on, so that will travel. So M2, this is M2. Look at this. So M2 is motor 2 going to the rightward, right? So that is the case also for the power circuit here. M2 to the right will become on, right? M2 to the right. So this one, the motor will travel here, now 20 centimeter going to the right. Of course, it will have a sensor here. Again, no? So there should be a sensor here so that it will sense that it already accomplished or finished the 20 centimeter rightward distance. So, and that is being exemplified by this I4. No? So that travel of motor will try to close this now because it will trigger the sensor now after accomplishing the 20 centimeter. It will trigger this, but this is already closed, so now it is energizing R3 or M3 in Siemens language. So M3, all the M3. So look at the M3 here. What will happen to the M3 here? So M3 here, I'll try to find M3. Look at this now. So this will be closed. And what is this going to do? So if this is closed, M4, now it is again the spray, right? The spray was off a while ago because of this M2, but now M3 will turn again the spray. Why is that? It's logical because the spray from here, no? So your spray gun is somewhere here, right? And this is the nozzle, and this is the triggering, what do you call this? The triggering handle, right? So the cylinder is here, okay? Right? The cylinder is here. So once the cylinder is here, so it will push, right? So it will go in that direction because the air will come here and then it will fill this up and then it will go into the rightward. So and then it will spray, right? So that's why it's here. Spray will be on. In this case, no? In this case, spray will be gun spray will be on, and then the other is for M3. Look at this, M3 here, right? M3 here, it will become close, no? So this one will travel here, the power will travel here, and then this M4 or the contact of M4 is closed, so no problem energizing M4. So what is M4 responsible for? M4 is responsible for going down. That is motor 2, right? So if you go to the relay side so that you can imagine more clearly, look at this. So here, look at this, no? M3 will be energized, so the power coming from line 1 will travel here and then travel here, R3, it will pass R3, and then this is already normally closed, so it will energize motor 1. Before motor 1 goes up, now it goes down because it will paint from top to bottom. So from here, it will paint at the width of 20 centimeter. Now that's because, that's because the coverage or the canopy that is being measured, no, by the spray gun as we have tested, no. So this one is 20 centimeter going down. This one, no, is 40. So but the width is 20. No, it will paint the 20 centimeter. That's why the motor that is responsible is motor 1. Now before it the motor 1 goes up, now in this case it's going down, no, after it travels rightward. So it will paint this uniformly, no, because that is what it is expected to do. So now, right now it will reach the bottom. So what will happen if it reaches the bottom? There's another sensor. No, there's another sensor here, so that when it reaches the bottom, the carriage, there's a part of the metal, no, some kind of metal triggering device. It will sense because this is inductive. Inductive sensor will sense the metal, no, or it could be also capacitive, no, depending on the sensing distance that you have used. So we're trying to see the situation wherein the motor that is going down already at the so-called bottom dead, no, bottom dead center, or the so-called the extreme bottom. So look at this. What's going to happen is it will touch the sensor, no, and in this case, look at this, right? So there's a sensor. Look at this. That is the I5 here. At the bottom, it will touch that, so that here is also latched, so it will travel here. No, so no problem. M3. Then it will touch the sensor at the bottom, sensor, so it will come here, right? And then already M3 is closed. then energizing M4. What is M4 responsible for? M1 down, off. Of course, it's going down, it should be off. Otherwise, it will continue. So it will turn off the motor, turn off the solenoid valve, of course, because the spray is also already done. No, why would you go spraying if it's already here? So it will just thicken the surface of the the um, the spray, no, coating. So it should spray off, no, spray gun off, motor down, motor 1 down, off, that's it. Then motor 2 right on. We are trying to make the motor triggers going to the right, no? So this motor 2 should go to the right. At what distance? We need another 20 centimeter. If you understand, the algorithm of our motion is this, no? Our displacement. So going up, spraying, then stop, then going here is 20 centimeter, stop spray, but the motor is active. The motor will stop here because there's a sensor. Then it will go down again. Now that's what we're doing. So when we're doing going down, it will spray, 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 spray until such time that it will reach here. When it reach here, the spray gun should stop. No, stop the spray gun, and also the motor 1 going down should stop, right? Because it's already here. So what are we going to do? Next, we are going to also motor 2 going to the right on, no, so that it can cover again 20 centimeter, and then it will go up again, and then it will going to the right. So on and on, no? So that's that's the path that we're trying to make, no? So going up, so it will spray here, yeah, and then 20 centimeter it will spray here, then 20 centimeter going to the right, it will spray here, then again 20, then it will spray here. Yeah, so that's the path that we are treading, right? So M4, all the M4 will be affected, right? So M4, so there will be a latch here, and then look at this, we are going to accomplish 3, no? Because of M4, we should put off the motor 1 down because it's already at the bottom, solenoid valve because we should stop the spraying, and we should go to the right because the motor 2 should go to the rightward direction. So let us see that in the power circuit, and our concern is M4. So look at the M4. So M4 is this. So here, this one is normally closed, it becomes open. Once it becomes open, the spray is going to be off again, because a while ago, previously, the current the immediate previous is it is on now because it's going down spraying. But once it reached the extreme down position, it will open, so the current will only up to be here, right? It cannot pass through here, so this one will be off because it's open. So that is spray off, no, because it's already down. So now it's down, and then what else? The motor 1 is down, then the this valve, no, this one is solenoid valve is off, and then the motor 1 is down. So look at the motor 1 here, motor 1, M4, right, right, this one, M4, right here. So this one is normally closed, it becomes open. Now when this is open, meaning the motor down is not active, right? It's off. Now because this one is for vertical, motor up, I sorry, motor down only, right? Because there is another contactor. No, they have different or dedicated contactor. One is going up, and the other contactor is going down. So another M4 that we should concern about is this. No, M4 should be closed. Why? Because this will travel M4. What is this going to do? It will pass the M5, then it will try to on the motor 2 because it's going to the right. Let me put here. No, first we go up, and then it travels 20 centimeter. Now this one is 40, this one is 20, then it goes down. Now it's already down. We're here now. Now it's the M2 rightward should be prepared again. Look at this, right? So when M4 is closed, look at this. Motor 2 is again active. So it goes another 20 centimeter, preparing for another round, which is uh, uh, 40 centimeter up, no? But we just put, no, let me emphasize that we just put one cycle, no, because we cannot show all the just for the purpose of academic um, demonstration. We just have this travel. Look at this. So first, then second, then third, then fourth, right? So next cycle is this. Now we just emphasize the first cycle, but it's a continuous cycle because the bus is very long. So we just put 40 by 20, no, 40 by 20. Now so look at this. It's 40, then 20, then we're ready, right? So another motion is this 40, then 20, then another 40, right? So we just have one cycle and then we're going to loop, no? There's a program in the PLC looping or the continuous cycle which will give us, no, the program that will continue to loop, no? So that is the established program. Then it will loop to cover all the length surface area with the surface area of the bus. So what happened here is we were able to explain in the relay pattern, no, as like a check and balance relay, the principle of relay, and then we translate it in the PLC because the PLC is using another language. This one is ladder diagram, that but it can also use function block diagram. But hand in hand, apple to apple, we were able to explain the relay ladder logic happening in the actual relay, and also the principle is the same when you use PLC because the relay is internal relay, no, electronic relay inside. So now the other information here is the address, meaning all the devices like the stop, start, and the sensors being used, and the solenoids, no, and the other outputs are Q, because in Siemens Q is the output, no. So let me have this. So when we talk of Q, it is the output, no, Q. Now here I is the input, no, I1, I2 inputs. Then the M are the so-called internal relay, no? M, the R. The R in the relay system is M here, M1, M2, up to M6, right? So that's why it's M6 here. So they are in the control circuit. This one is in the power circuit. So when we do all this, now we could put them in a sort of BOM, meaning BOM, bill of materials format, so that we could have the item and all the description, and then the quantity, and then the so-called projected cost in pesos. So all in all, our I think we have this total I think 60,000 something, right? So now the significant findings for this is this. The spray painting machine outputs in terms of uniformity. The Palofing table showed the thickness from a mixture of paint 8-liter normal or 4-liter hardener and 2-liter thinner on a sheet metal of 0.4 by 0.4. So we did use the zero point 0.4, no, by zero point 0.4 because we're trying to ready the next cycle, right? Ideally, our dimension should be only 40 centimeter by 20, no? But we just extend because we want to paint this, no, for the next cycle. So we paint this up to here, now then we travel here, we paint this up to here, right? Then we travel here. So we need another 20 so that it can go somewhere here, right? So that's why point 4, point 4 by point 4, which is 40 centimeter by 40 centimeter. Now that's the sheet metal that we use for both manual and automated spray painting by taking 8 points as a reference. So 8 points as a reference. We're gonna discuss that now for measuring. Now, so we have 8 points: 1, 2, 3, 4, 5, 6. Now, 4, 5, top, and then another 3. Now, so for this point, we'll get the measurement 3 times. So 3 times, and then we get the average. We'll jot it down. Then we get here the 3 times. Then we average it. Then we put it in the measuring sheet, right? So there's a comparison. We have a table for comparison of thickness coating using manual and automatic. And then this is the conclusion or the interpretation. The rate of coating variation is decreased from 0.0019 to 0.0012. Therefore, the newly designed spray painting machine brings uniformity improvement at least by 36.84%. How is that? We have a table, as I said, there's a 5.1. I think this is the 5.1 because this is 5.2. So this is table 5.1. I was able to crop, sorry. But this is table 5.1. So coating thickness, as far as coating thickness is concerned, no, we have a standard for measuring that that is dry film thickness, and there are two ways to measure that. I mean, in terms of units, one is micron, and the other is in mil, which is 1/1000 of an inch. No, so both are being used. This is metric. The other is in inches. So look at this. Now there are 8 points because we're trying to use the standard. Now there are two standard that is most popular. One is ASTM and the other is SACC. I think we have here SSPC. Sorry. So SSPC. Then this painting. No, painting coating thickness 2. No, I think there's a version 2. So this is the standard for measuring. That is what we use here in our evaluation, no, validation. I mean, so SSPC. Okay, SSPC. Sorry, this one is SSPC. SSPC. Now, so we have a standard. So this is the so-called probe for the measurement. So we did use that. We borrow from the company, from the Bishop the automotive industry, and they have this uh, the so-called thickness, no, coating thickness, electronic uh, measurement device. So look at this. For the manual painting that we have tested, we already have gathered data, and that is here, right? So this is 12 and 14. Now for 8 points, now 5, 7, 6, 19, 13, and so on. Now there's a random result for the coating thickness in microns, but in automatic, look at this now, 15, 17, 16, 15. Now, so look at this. There's a an even or an uniform thickness here in terms of microns if you are in manual, but here it's almost consistent. Now there are only variations of 1 or 2 or 3, no? 18, 15, 17. So meaning from 15 to 18 microns. And then if you total this, if we're going to have a total of this, no, so and then it will have a summation of 86, right? And then this one is 129. So if you are going to get, no, this because it is in microns, 12 microns, so this one is already a point something in millimeter, no? So 1000 of a millimeter. So this is gonna be 0.12, 0.5, and so on, so on. So it will have this one, right? So 0.16 divided by 86 is 0.0019, and this one is 0.16 divided by 129 is 0.00112. So the percentage decrement in variation of coating, no, it was lessened, no? The variation was lessened with 36.84. That's one validation. The other is in terms of manpower. How much labor did we use? Now, for workers needed to feed the paint of the spray gun, so it needs two in the manual. This one automated is one only, right? And then workers participating in painting activities, it needs three. This one is enough, no, one person. Workers needed to carry the painting accessories both sides of the bus, no, so this one is three. So many accessories. This one is one because we have a roller for the they that base, no. So it's we have a four roller, one for each leg or peg, no. So if you're going to have this, now let me show you the just the calculation for the benefit of everybody. This is if you're going to total this, this is going to have an total persons is 8. No, this one is 3. No, for example, for the whole process. No, from uh, from from filling the spray gun, from painting, and for lifting or carrying the accessories. So what's going to happen is this, right? So 8 minus 3, the higher minus lower divided by 8. So we'll have a 60.5 reduction in terms of labor. So that's a good number for the reduction of labor. So this one I showed it to you because dry film thickness, there's a measurement and there's a industry standard for this. There are three, no, but I was not able to put the other one, but it's more of SSPCPA2 standard and ASTM. So it discusses the procedure of testing and measuring the coating thickness there. That's why we use this standard for getting the measurement. So just additional information. For example, if you're just doing primer and mild, no, meaning in the medium and top coating, you will have a kind of reference thickness for this. Now, for example, for primer, 75 or 100 microns and 50 microns. If you are using this type of coating, epoxy zinc, epoxy polyurethane, and so on, no, water-based, epoxy polyurethane, and whatever. So this is in terms of micron, meaning thousands of millimeter or millionth of a meter. So this is going to be point, no, point 75, right? Because this is micron, right? So this is 0.75 uh, millimeter, right? Because this is meter, right? Micrometer. What we have is millimeter, so we divide again by the thousand, because this is 1 is 10 to the negative 6, no. So that's the case here. So my point here is just there is a reference or guide when you are doing the primer or the medium or top coating, because there's different layer before you finish the coating, no. So same thing here. It just want to show that the average thickness for the material. For example, industrial primer per coat. So in mil, 1 mil, no, 1,000 of an inch. This one is 25.4, 1 millionth of a meter. So it's gonna be microns. No, so this is microns, a millionth of a meter. Then you can have it like thousands of uh, millimeter, no, in a if you're going to have it in millimeter. But this one is millionth of a meter. No, then you can convert this into thousands of millimeter. This one is millionth of a meter. So this is meter, then you divide by million. This is a meter, then you divide by 1,000. So, and you will get millimeter. This one is, you get the meter, right? 10 to the negative 6 meter, right? So it's just, there's a comparison. As you can see, industrial enamel. So look at this, yeah. Industrial primer per coat 25.4, and this one is 50.8. So I think our range is yeah, at this portion, 25.4. So look at this. Look at this. Yeah. So 25 or less, no? So 17, 18, yeah, like that. So we are in the within the standard, no? So now we go to the recommendation or summary. So to summarize this, we were able to accomplish, no, a project work. It's still there in the university that I am serving for 8 years. It has been there. I think they are gonna studied it for future use. So we were able to automate the spray painting in a robotic manner, but just in two axes, that is horizontal and vertical only, no, X and Y. So we're not able to do the Z and the other, like the cylindrical or the the spherical. Now, so but the result based on the thickness uniformity is there in the table, and also the reduction of the required manpower is there. So uh, we were able to have this because of the so-called mechatronics discipline, the marriage of mechanical and then electronics and the programming or the IT. So in this prototype, we were able to do the wiring, no, the wiring diagram using relay, and then also the programming using the Siemens. So that is what has been done in this project. And then there's an equal distribution of paint on the bus body as based on the measurement on the 8 points, and then averaging 3 times for each point that we have used. So the conclusion is that from the data collected, now the performance of existing spraying system affects the uniformity of the whole process. Painting is determined by the atmospheric pressure around the room to have relatively good painting outputs. Also, the painting or the wind speed or velocity or the pressure should not interfere, or should not matter in the painting. Otherwise, if the wind is very strong, it will affect also the performance of our automated painting system. The speed of painting activity is also determined by the operators, right? And then from the design analysis, the following points can be concluded. Because of the design system, spraying mechanism is scaled down or prototype, and single number of spray gun, the length of bus to be painted is limited to the maximum of 40 centimeter. As I told you, 40 centimeter upward and 20 centimeter horizontal, no? Because due to resource constraint, no? Because it's just for academic, we just have this 40 by 20, but to extend by 40 by 40, no, to prepare the next motion, no, so that it will become have a loop, no. So we could continue the program in looping and also the motion, no. But for this kind of project, we just tested a limited, no, so 20 by 20. So here, here, and then here, no. So since proper arrangements of each component are well analyzed, the component of spray painting mechanism is not affected by motions of the spray gun, no, because it's stable. The motion of carriage with the spray gun and length of bus to be painted is calculated as per spray coverage area, also properly interfaced. Now, so the conclusion, manual actuating on the trigger spring over the flat surface of the bus is completely replaced by automated spraying mechanism. The spray gun uses an existing feed of paint and keeps a fixed distance with the surface of bus. So we have a distance, no, based on the pressure of the given by the compressor. Sensors are enabled to sense the driving knot to stop when it reaches the required points for both vertical and horizontal directions of the flat surface of carriage, meaning it defines the limit, travel limit, no, both for the X and Y axis. The quality of spray painting is improved by the uniform motion of the spray gun, as well as the continuous force applied on the trigger by the actuator till the required length is reached. Arrangement of machine is ergonomically fit with the operator, and safety also assured since no more operators to participate while painting the bus, or there's only a minimum of one, no, and then it lessens the requirement of the labor, and also it was ergonomically designed. So recommendation is that we recommend that the spray painting operations with the designed operating parameters and conditions be used. Further recommended that the other related established manual spray painting system standards be kept so that good painting output could be achieved to its optimal performance level. Another recommendation is another axis, the z-axis, now before because in this study only x and y, so we should focus also on the next or next level z, no, so that it becomes a 3D three-dimensional painting system. So the z-axis we could focus more on the study on the next level or on future work, the 3 dimensions, no, to achieve. Another study is be focused on the cylindrical and the what do you call that? Cylindrical, and the other is spherical. Now, spherical movements, so that 6 degrees of freedom of movements must be realized, much like that of a modern car painting system using full functional robotics, like that of like maybe of Toyota or Mitsubishi or this Porsche. Now, those are degrees of freedom, uh, 6 degrees of freedom. So, 3 4 to 3 4 translational, and then 3 4 rotational, no? So it becomes 6 degree of freedoms in space, right? So the future works are this, no? So the base frame, which carries all electromechanical accessories for a painting system, should have a wheel. So that is what, because what we have done is just like a C section, no? So we should put a wheel so that it's a lot easier to transport from one place to another, no? The wheel, of course, must be driven by electric motor so that it's going to be easy to transfer from one place to the other. The components of the mechanism will be built up in a large scale. That's another future work. It should be like a life size, meaning the actual based on the height and the area of the actual bus, no? That's going to be on the future, and multiple spray guns should be ready to spray the paint or maximize the volume of a spray gun or paint tanker, and producing a number of holes on it to increase the spray coverage area so that completion of painting time will be minimized. So variety of design, another recommendation, should be taken into consideration to produce images on the required surface to make color painting in order to achieve aesthetics of bus body. Because right now, we only concentrate on the mono, no? Mono, mono color, monocolor, that is only one color. What if you put color of different type? So the system should accommodate that. That's another future work for this project. And then for also for contour, for example, if your design is curvy, with curvilinear or contour, so your paint spray gun or robotic spray gun should follow that contour. And our robot is only Cartesian, no? Cartesian means rectilinear in X, Y, and Z, no? But if curve, like that, or some design, it is not, it's no longer capable. So that's we include this in the future work. The other is finally the Department of Design and Development of the automotive industry. That's the industry there for the bus and the military buses and the commercial cars and buses. And METEC, or the Metals Engineering and Technology, Metals Engineering Technology Corporation Research Center should take into consideration on these important future works to perform the operation properly without any difficulty, and to improve them so that the output of the automated bus body spray painting machine will be optimized to its highest or maximum level. And that ends our presentation for this robotic or automated uh, bus body spray or robotic spray, for uniform surface thickness. So again, this Engineer Charlton as Inaw, and in behalf of my co-researcher, Engineer Ahmed Endris, we are thanking the organizer of this assembly or conference. No, so thank you very much, and have a good day.